So here we have a parabolic surface or a paraboloid, and we have 81 different particles that are going to fall down, hit the paraboloid and be reflected off of it. What you'll notice when they're reflected is that they're all going to converge to a single focus. So this is a very useful property of paraboloids, and this property is actually used in a lot of applications. Now, as this simulation runs, the camera is going to move along with the particles, which is why the paraboloid's doing this weird shape. So just bear with that. I will get rid of the camera moving in a second. So one application of this property is in satellite dishes. You have photons coming in from outer space, usually microwaves or radio waves. And you want to try and focus these as best as possible to a single point so you can get a very clear, very strong signal. Satellite dishes need to be very wide because they're picking up long wavelength light as opposed to narrow wavelength light, which can be detected with smaller receivers in theory anyway. You might still want a big dish just so you have better chance of collecting the photons. So they come in from outer space, they hit your satellite dish, and they are reflected down to a single focus, and then the dish will take that as its signal input. Another unique property is that once they've passed through the focus, and anything that emits from the focus will then hit the paraboloid, and it will be reflected in a direction that's going to be perfectly parallel to its initial trajectory. So all of these points in this little ring, which looks like something that you might see in a hyperbolic surface, all of these little points are moving in the same direction. They're all moving perfectly perpendicular to the XY plane. And that's used in things like torches. So you might notice that a lot of torches, the little reflective surface isn't a perfect sphere. It's going to be more parabolic because you want that light to be directed in a single direction, right? You want it to be directed. And the best way to do that is by putting your light source or the bulb at the focus and then letting the light rays hit the paraboloid and move in a parallel motion like this. It's also used in things like audio equipment. If you live in the Netherlands, there's a really cool demonstration of it in the Nemo Scientific Institute. They have these great big parabolic reflectors that are separated about 10 to 20 meters apart. You can whisper in one end, and over a long distance in a very busy and noisy room, you can actually hear somebody whispering from 10 to 20 meters away using these parabolic reflectors. So that's cool. They are some applications. Obviously in the audio equipment, you would use it to pick up sound signals that are coming from far away that might be quite soft. I'm now going to go through how this program actually works. Okay, so as I walk through the explanation, I will just let the simulation run on in the background. Now I've got it working with gravity. So the balls are going to bounce around off the surface and move as if they were just falling balls falling due to gravity. The ground or the surface itself is a paraboloid, so this is the equation of it, x squared plus y squared. It's all been dilated by a factor of 0.1 and shifted down by 2 units. The only reason I've done this is because it better fits within the Desmos home, like the homing setting. If I want to see it more clearly, I've just got this little feature where I can just show a grid of the surface. That way I still have a basic idea of how the surface is curved, but I can see through it a little more clearly to see what each of the balls are doing as they're moving around. The way this works, or at least the way I've detected whether or not a ball is bouncing, is I've calculated the vertical distance between each of the balls and the surface. So P of Z represents the height of the ball, and then F of Px, Py represents the height of the surface. When that difference comes within 0.05, this little delta function will flick from a 1 to a 0, which we just saw happening there. When it flicks from a 1 to a 0, that tells my program that the ball has hit the surface and that it should then change direction of its velocity. Now, how do I know which way the velocity should go when it hits? Well, the way I've gone about this, and there might be other ways to do it, I'm not sure, is I've calculated the normal vector corresponding to each of these points. So on the surface, it has its own particular slope, and I can find the slope, or I can understand the slope by finding the normal to the surface at that point. So let's pause my simulation to explain exactly what I mean. At each of these points, and we're going to turn the surface back on now. At each of these points, I can think about a shadow on the surface. So all my colored points will project a shadow, which is represented by the purple points on this black surface. At each shadow, the surface has its own unique slope. And sorry, because this is a two-dimensional surface, there's actually many different directions I could think about the slope going. For example, I could think about the slope along the x direction, which will be represented by these gray vectors. So at each of these little points, the slope moves according to these gray vectors along the x direction. But I don't just have to think about the x direction, I could think about the y direction, or I could think about any combination of x and y. It turns out that x and y are just the easiest in this particular example. The reason why is I can get these slopes using partial derivatives. So the partial derivative at x, or the partial derivative with respect to x at AB, tells me how far it's going to be moving in the x direction. If I multiply that by some small delta, which in this case delta is just 1 over n, then that's going to get a better and better approximation as n goes to infinity. The change in z is then just going to be a plus this delta f, evaluated at f, minus f of ab. So I'm pretty much taking the definition of a derivative, and I'm just using it to calculate how does the slope change over a very small difference, 1 over n. So if I make n get gradually bigger, we can see that these vectors become smaller and smaller until essentially they're no longer visible. They are still there, but now they are much, much closer approximations to the true slope of the surface. But let's just bring n back to 1 for a second so we can actually see these vectors. When we take the cross product of f and g, that's going to give me a bunch of normal vectors, which are shown here. And here I'm just showing the unit normal vectors. These tell me in what direction the slope is changing. I can use these normal vectors to help me calculate in what direction a reflected ball will bounce. So let's just bring that n back to 100, and I can turn these off because we can't even see them anymore anyway. So n is f cross g, and nu is just my unit normal vector, in case you're wondering what that is saying. When the balls come down, so let's run it for a little bit, the balls are moving in a downward fashion. I can think about their reverse velocity. So close that. I can think about the opposite velocity to the balls. That's represented by these green arrows. So as the ball comes down, it has some velocity. The green arrows just show the reverse, because when that ball eventually hits the surface, it's going to be reflected and it's going to bounce back up again. So instead of thinking about its actual velocity, which is going down, I'm thinking about its negative velocity in all of these calculations, because that's the thing that's going to be most useful. So we have negative v. That's the direction of this green arrow. I want to figure out, okay, the ball's going to come down and it's going to be reflected perfectly, because I'm assuming these are perfectly elastic conditions where no energy is lost, where momentum and energy is conserved within the ball. It hits the surface and it bounces in a perfect reflected fashion. The way I've gone about finding this new direction is using the projection vector. So I can project the green vector onto the white vector. That's going to give me the component of the white vector that's parallel to the green one. That's useful because then I can use that to find the perpendicular vector going from the green to the white vector. This perpendicular vector is just going to be the projection minus my green vector. So the green vector is negative v, so then my perpendicular component is going to be proj minus v, or in other words, it's just the projection plus the velocity vector v. If I want to find the reflected vector, I just need to add this to my projection vector. So really what we end up with is we end up 2 times the projection vector plus v, and that's going to give me my final velocity after reflection, which is what this calculation here is actually doing. So we can represent that with these blue vectors, and they show me where the ball should go after it's been reflected. So it comes down and it should be symmetric with respect to that grey normal vector in the middle. Now what's good about this is that it actually doesn't matter which direction my normal vector is facing. So as you know, when you take the cross product, sometimes the vector is positive, sometimes it's negative, depending on the order of the vectors that you're cross producting. I don't know what the present participle of that would be. Maybe the vectors you're taking a cross product of. Let's center that back again. So it doesn't matter whether these vectors are pointing up or down. Oh, sorry about that. We can see here with these ones on the left that even though the normal vector is pointing away, the green and blue vectors are still symmetric about that normal vector. So that's what's really useful about this particular construction, is that I don't need to think about which way the normal vectors need to point. They can point any direction as long as it is perpendicular to the surface. So that's really helpful. So now that I have VF, I can then just put that into the code and use it to calculate the direction of the balls. So the velocity changes according to the acceleration. Your velocity is just your initial velocity plus acceleration times d. So d is a small step in time. Essentially, your acceleration is your change in velocity over change in time. So if I multiply acceleration by a very small difference in time, that's going to give me the very small difference in velocity. The smaller I make d, the more accurate this simulation is going to be. The downside to that is, of course, that if I make d really small, the simulation is going to move very slowly. I can make d bigger, and that will speed up the simulation. The issue with that is if I make it too big, then the time steps are just too large and the simulation breaks down because it can't detect everything with the accuracy needed to properly simulate things. So there's a bit of trial and error in determining an ideal value for d, and it will change depending on your initial conditions. At the start, I used d equals 0.16 because there wasn't acceleration. I didn't need to worry about the ball speeding up too much. Now, I use this delt function that I spoke about over here. When the balls are close enough to the ground, delt goes to 0. So that means that these first two terms are treated as zeros, and now the VF term is all that's left. So when the ball is close to the ground, the velocity goes straight to VF, which was this velocity that we calculated down here. VF is twice the projection plus V. And that's going to flip my velocity to the new one, which is the reflected velocity. The change in position is then very similar to the change in velocity. So it's my initial point plus d, my small step in time, multiplied by v, the velocity. So again, velocity is just change in distance over change in time. So if I multiply velocity by a very small change in time, that's going to give me a rough change in the distance, and I can just add that on to p. The one exception, of course, is if it's close enough to the ground. Now I don't want it to keep going in that direction v. I want it to go in the new direction vf. So I make the ball move away from the ground. And that's pretty much how this all works, right? Like down here in balls, we have the initial position vectors for the balls. So this creates a 9 by 9 grid of balls that all start at a height of 3. This just gives me the color palette for the balls. I can change that by changing the number at the front. I just like that palette in particular. We also have our initial velocity, so if I want to give the balls some velocity, I can. I can make them bounce up, for example, at the start, so that they'll move like that instead, and they'll just do their thing, bounce off the surface as they normally would. I can also change the initial acceleration. So we see that we have acceleration here at the moment. If I wanted to, I could make that 0, so that when I reset it, it'll be a simulation with no acceleration instead of negative 9.8. So yeah, this is linked in the description. I made this inspired by another video that I've also linked in the description, which I thought was really cool. I was sick the past couple of days and I had nothing better to do with my time than program a bouncy paraboloid in Desmos. So I hope you've enjoyed. Thank you for watching, and feel free to play around with the link in the description.